All right, so in chapter 6, we talked a lot about reaction kinetics, thermodynamics, things like this. I'm going to give us an example reaction, and I want us to try to come up with some conceptual experiments. So in this reaction, I'm going to have some sort of carbon-based compound, and it's going to have what's called a leaving group on it. I'm going to abbreviate that as Lg. And then for my second reagent, I'm going to have an Nu. That's my abbreviation for a nucleophile, right? And in this reaction, the nucleophile is actually going to swap off and replace the leaving group. This is called a substitution reaction because of that. So we're going to kick off that leaving group. When the leaving group gets kicked off, it also takes electrons with it and has an overall negative charge. So this is the net reaction for a substitution. The question is how this mechanism actually works. And so we've got a few different options. Option 1. So let's look at this one and let's say, okay, if we've got a leaving group and a nucleophile hanging out, maybe what happens is in the first step, the leaving group just kind of pops off. If the leaving group pops off, we're left with a carbocation. We still have our nucleophile floating around. And now we also have our leaving group floating around also with the negative charge. So that's one option. What do you think the next step is going to be to get to our final product? Yeah, the nucleophile in this case is going to be really attracted to that positive charge. In this case, that carbocation is going to be an electrophile. It wants the electrons from the nucleophile. Why doesn't the leaving group attack back in? Because then we'd just be going back to starting materials. The reality is sometimes these are under equilibrium conditions. I'm just showing it as a single-headed arrow. Okay, so now we've got this. We've got a new covalent bond with our nucleophile, and we've got a leaving group kind of hanging out over here with its own negative charge. So this could be one potential option for this overall reaction. Let's try to come up with a reaction coordinate diagram for this, where we've got Gibbs free energy over here. We've got reaction progress over here. Let's think about the first step, right? So that first arrow, meaning this arrow right here, is going to have a reaction hump. Will our carbocation be higher or lower in energy than our starting materials? Higher. Okay, so I'm going to put starting materials down here. And we're going to have a hump that goes like this. And that's going to be our carbocation intermediate. So I'm just going to label this as intermediate right here. I'm going to label this as starting material. And this set is going to be our products. All right. When we think about going from our intermediates to our products, assuming this overall reaction is going to be spontaneous, our products have to have a drop in Gibbs free energy, so they must be more stable than our original starting material. And there must be some sort of activation energy. So let's go like that. All right, so if we think about this, we've got a couple of things to consider. We've got this first hill we have to climb. We're going to call this EA1, right? And then we also have a second hill we have to climb over here. It's kind of a little speed bump mostly. And we're going to call that EA2. And when we get over to the very crest of that first hill for EA1, we have this double dagger here. What's that called again? Transition state. So that's when the leaving group is halfway broken off. Yeah. What's that? Yes, the two humps are going to be at slightly different levels here. The first hump, the red hump, is going to be higher than the second one. Okay, and then we also have a second transition state where we're going from our intermediates to products, where that nucleophile is halfway forming a bond with that carbocation. All right, what do you think the rate limiting step is going to be? EA1. Okay, so EA1 is rate limiting because it's bigger. All right, pretty simple concept right there. So that's going to be our rate determining step. All right, if you've got the bigger hump, that's the thing basically limiting the speed of your overall reaction. All right, so let's try to abstractly come up with a rate equation for this. So if we think about step one, meaning this whole side of the equation, oh, that didn't work well. If we think about step one being this whole side of the equation being rate limiting, what concentration do you think matters the most? Does the nucleophile concentration matter? No, it's not actually participating in that first step at all, right? So the concentration of the nucleophile doesn't impact the overall rate of this first step. What does matter is this one over here, right? So the starting material with the leaving group. So the rate for this reaction is going to be little k times the concentration of our thing with our leaving group on it. The nucleophile is not going to play into this in any way, shape, or form, right? All right, so this is one specific type of substitution reaction. This is called a first order substitution. Does anybody know why? Because it's a first order reaction, right? It's pretty clever. So it's a first order substitution. That involves a nucleophile and I'm going to abbreviate nucleophile. And so what we oftentimes call this is S sub N1 to indicate that this reaction is first order and involves a nucleophile. I actually showed you this a little bit last week when we were talking about reaction orders, right? So this is one theoretical option for how this overall reaction takes place. Does that make sense? Okay, now let's compare this to a competing reaction, another potential option. And option 2 is going to be a little bit different than option 1, but it's going to involve the exact same starting materials. So we're going to have our nucleophile, our thing with the leaving group on it, but instead of the leaving group falling off and then the nucleophile attacking in, what's going to happen instead is the nucleophile is just going to attack and basically knock off that leaving group all in one step. So you can almost think of it as a malicious shove, right? So it's going to hit the backside of this and knock off that leaving group. Actually, let me change it a little bit. So that's another option, right? In this case, we're not going through a carbocation at all. Yeah?
Does that only work if Lg is incredibly negative, or could it just be a non-polar bond and you be incredibly...
That's a great question. So you were asking about the leaving group itself. We'll get into that. Right now, we're just keeping it super generic and comparing two reaction pathways that might occur. But there's a lot going on with these reactions. We're just kind of skimming the surface. Yeah, we're just going to look at the reaction orders first, and then we'll go into things like, what about the nucleophile? What about the electrophile? What about the starting group? What about the solvents? What about temperature? What about this? What about that? What if it's Sunday? There's a million things we have to pay attention to. All right. So let's think about this reaction pathway. We're going to be going from starting materials to products. In this case, we're not going through any intermediates, and assuming this reaction is spontaneous, it's going to look something like this. So we'll have starting materials over here. We'll have products over here, but no intermediates, right? Okay, so when we look at this, we're still going to have an activation energy, a hill we have to climb, but we don't have to worry about one hill versus another hill. It's just going to be one hill. So this is our starting material. This is our products. All right, now what we need to do is to figure out the rate equation for this reaction. Does the concentration of the thing with the leaving group matter? Yeah, absolutely. Does the nucleophile concentration matter? Yeah, because this reaction involves the collision of those two things, right? So if we think about the rate now is going to involve the nucleophile concentration times the concentration of the thing with your leaving group. All right? The rate limiting step in this case is what? How would you describe that abstractly? Yeah, it's going to involve the nucleophile colliding with the other starting material. And the other one, the rate limiting step, was the leaving group just falling off on its own, not being shoved off. So that's a fine difference, but an important one. So I'm going to call this rate limiting step RLS. Involves the collision of Nu with a negative charge with our other starting material. Whoa, that doesn't look very good. All right, so if we look at this overall reaction rate, it's got to be a second order reaction. So this is going to be a second order substitution that involves a nucleophile. So just like before, what we're going to call this one is SN2. So we've got two potential reaction pathways. One is first order, one is second order. All right? Yep.
Could both options be happening at the same time?
That's a good question. Could both options be happening at the same time? Experimentally, how could we check? Yeah, so let's try to come up with some sort of theoretical game we could play with this reaction by manipulating concentrations and seeing what effect that has on the reaction rate. All right, let's say I double the concentration of this leaving group. Does that help me at all? Well, let's say I double the concentration of the thing with the leaving group for the SN2 reaction on the bottom. What will happen to the overall reaction rate? It'll double, right? So if you double that, it will double. All right, let's go back up and look at the other one. What happens to this reaction if I double the concentration? It'll also double. That doesn't really help us at all. So doubling the concentration of the thing with the leaving group doesn't experimentally provide us any sort of evidence that helps us figure out which reaction pathway is probable, right? All right, what we could do, though, is let's double the nucleophile concentration, right? If we double the nucleophile concentration for option 2, the rate will double, right? What about option 1? Zero effect. So experimentally, we have a way of determining which one is more favorable over the other. In general, it's not going to be a mixture. One will definitely occur, one will not occur, and you'll be able to determine the reaction rate. If there was a mixture, what do you think would happen if you doubled the nucleophile? It might not double exactly. It might be something like 1.5 or something like that, in which case you could argue maybe there's a mixture. All right, so let's make a note. If you double the concentration of your nucleophile and ... the rate doubles, then the reaction is an SN2 reaction, basically meaning it's going to involve the collision of your nucleophile with your leaving group and kick off your leaving group all in one step. If your rate is unchanged, then that implies that it's got to go through an SN1 route based on our understanding of the possible reaction mechanisms. Does that make sense? For me personally, this is my absolute favorite area of organic chemistry. This is called physical organic chemistry, where you know what the starting materials are that you put in, you know what the products are that you got out, and then you're left wondering, how did this happen? And you have to come up with experiments that you can test out to prove that one mechanism is not the case, and then infer which remaining mechanisms are most probable. Does that make sense? All right. So we've got a lot to think about here. There's a lot, but bear with me. Next thing I want to do is to talk about that thing with the leaving group. This is most commonly referred to as the substrate or the electrophile. And so let's compare that for an SN1 reaction. Yeah, it was the thing that had the leaving group on there. So consider the reagent that has the leaving group. Okay, so option A, I'm going to put down here. Let's say it looks like this, and we've got a nucleophile. And then option B down here has a leaving group coming off of a tertiary carbon, and then also a nucleophile hanging out. So in an SN1 reaction, what's the first step going to be? Leaving group falls off. So let's just go ahead and draw the reaction mechanism for each. So for reaction A, the leaving group will fall off. You'll be left with this carbocation. Your nucleophile is going to be hanging out next door, and your leaving group that fell off is now going to have a negative charge. Okay? If we do the same thing for the bottom one, we can kick off that leaving group. We now have a carbocation. Same idea, we've got a nucleophile hanging out, and we've got a leaving group with a negative charge. And then let's finish that last step. In the next step, what's going to happen? Well, the nucleophile is going to reach over and attack into that carbocation center. And the leaving group is going to hang out with its negative charge. All right. Which reaction pathway do you think is more favorable? Reaction pathway A or reaction pathway B? A? Oh. Check with your neighbor and see if you can argue your way through this.
Bothers me because it's going to be very situational based off of that's what I'm having trouble with.
All right. Let's check in. Who thinks A is going to be more favorable? Who thinks B is going to be more favorable? Oh, this is good. I like a debate. All right. So let's do A on the reaction coordinate diagram. If we think about the intermediates here, right? So meaning these blocks, which one do you think is going to be higher in energy? Reaction pathway A or reaction pathway B? A is going to be higher in energy, right? Okay, so let's think about that. If A is higher in energy, I'm going to do that spot in blue, and I'm going to do it up here. And then B, I'm going to put down here as the lower energy intermediate, right? If we think about the strength between the carbon and that leaving group, it's going to be roughly the same, so it's going to require about the same amount of energy to break. So for this reaction pathway hump, it's going to look like that. For this one, it's going to look like that. So if we think about which one has the lower activation energy, which one's it going to be? B. It's a lot easier to break the bond for the leaving group in B because we're resulting in a more stable intermediate, right? In that case, the carbocation is tertiary. We already said that tertiary carbocations are more stable because of what feature? Hyperconjugation, right? So in this case, the rate limiting step for reaction pathway B has a lower activation energy. It's going to be a lot more likely to occur. And then just for the sake of argument, let's finish out this reaction pathway. And we'd say this has a lower EA. And another way of thinking about this, let's just do this. Sorry, circle this one. Is say this reaction is favorable since it goes through a more stable intermediate, specifically a more stable carbocation. All right, yeah.
So looking at the second half, wouldn't reaction A, like, wouldn't that carbocation be more prone to get the nucleophile?
Yeah, so you were asking about, all right, the next step, what about that? It's not rate limiting, so we don't even consider it as important, really. We know it happens, but it's going to happen fast for either reaction. Yeah, good question. All right, so that kind of leads me to my next point, is let's make a box here. We've got tertiary carbocations, which are more stable than secondary carbocations, which are more stable than primary, which are more stable than methyl. And we can even put in resonance up here. Actually, I'm going to slide this over. But resonance is the most stabilizing feature. And like we said the other day, we could say these are more stable carbocations going to the left. Another argument that we just made was that this increases the likelihood of an SN1 reaction, right? All right, so if we think about this, if we had, let's say, a methyl group with the leaving group coming off of it, it's highly, highly unlikely that it's going to go through an SN1 reaction because it has no hyperconjugation to stabilize that carbocation, right? So it makes a lot of intuitive sense. Does that make sense? All right, let's think about SN2 reactions. So we just did the SN1 reaction. And we're again going to consider the reagent. Oh man, my handwriting is terrible today. With the leaving group. I know. Longer you're in school, the worse your handwriting gets. All right, so we've got reaction A. And in fact, I'm going to do the exact same reaction that we did before. And we've got reaction B underneath it. That's the other reaction. It's different. In an SN2 reaction, we said that the nucleophile is going to slam into the other starting material and kick off the leaving group all in one step, right? So what I'm going to do is show that using tandem arrows, right? So hit that carbon that has a leaving group on it, and then kick off that leaving group all in one reaction. All right, for the other one, same idea. Do that, and we're going to swap off that leaving group for our nucleophile. All right, which reaction pathway do you think is more favorable here? Check with your neighbor and see if you agree. Yeah. All right, who thinks reaction A is going to be favorable? Who thinks reaction B is going to be favorable? Again, some debate. I think debates are good. All right, imagine you're that nucleophile and you have to run into the carbon, right? So let's even highlight the carbon that we need to attack. We need to attack this carbon, highlighted in green, right? If you're a nucleophile and you need to run smack into that carbon as hard as you can, you don't want things in your way, right? So I often think of the stuff coming off of that carbon as defenders protecting that quarterback, right? The more defenders, the harder the time is for you to run into that carbon. Yeah?
Aren't there also hydrogen coming out of it?
There are, but what takes up more space, a methyl group or a hydrogen? Yeah, if I'm going to try to sack a quarterback, I'd much rather their defenders be itty-bitty, right? So in this case, trying to be the nucleophile and run into that carbon, I'd prefer for there not to be much stuff hanging off of that carbon. I'm going to have a lot easier time. Yeah?
Could it also be that the electron density is more pulled towards the leaving group than the first one, where it's that shared between the carbon and so the nucleophile point?
So you're asking about polarity?
Yeah.
Yeah, in this case, we're going to assume that the leaving group is roughly the same electronegativity. So we're going to assume that the bond polarity is going to be roughly equivalent. The bigger factor here is something called sterics. So if you think about all of these groups, they're kind of in the way. Hydrogens are itty-bitty, but methyl groups take up a considerable amount of space. We would call this one sterically blocked. Or sterically hindered. All right. So if we think about this in an abstract sense, we could have a tertiary carbon, we could have a secondary carbon, we could have a primary carbon, or we could have a methyl carbon. And if we think about the bulkiness of each of these, we would say, well, a methyl group's definitely less bulky. And that increases the likelihood that an SN2 reaction will occur. It's pretty convenient, though, because if we think about these trends, they're flip-flop from one another. SN1 reactions are more favorable with tertiary carbons than they are with methyl groups, where this is more favored with the methyl group over a tertiary carbon. Yeah?
So does resonance not play a factor?
Yeah, that's a good point. Does resonance really matter in this case? Well, we're not dealing with carbocations, so it doesn't really matter in this case very much. You can do... Let me not even go there. I'm going to confuse everybody. All right, moving on. Let's think about some of the other things going on in this reaction. There's a lot more. Let's talk about the stereochemistry of each of these. So stereochemistry matters a lot. Let's do SN1 first. And what I want you to do is to help me draw this molecule. I've got R, 3-iodo, 2,3-dimethyl, excuse me, 2,3-dimethyl pentane plus a Cl- nucleophile. All right, so let's first draw that starting material.
Yes, I'm happy now.
We've got a pentane, so I'll go ahead and draw 4 or 5 carbons on there, and we can quickly number this. Oops, that should be a 3. And coming off the 3 position, I'm going to have an iodine. So I'm going to just plug in an iodine right there. Off the 3 position, I also have a methyl group, so I'll put that on. And off of position 2, I also have a methyl group. All right, now what we need to do is we need to assign dashes and wedges because we do have a stereocenter. Okay, so let's go ahead and do that. All right, like I said before, if we've got a stereocenter here, one of the easiest ways guess and check, right? So let's go ahead and make the iodine a wedge and the methyl group a dash, and then check. So I'll move my iodine to a wedge and my methyl group to a dash. Is that going to be R or S? I'd say that's R. I got lucky. I guessed and checked and got right on the first one. If we assign priorities, we've got position 1 here, 2 here, 3 here. Go clockwise around, lowest priority is a dash. So it looks like it's an R to me. So we've got our starting material set up. All right, we also have chloride hanging around as our nucleophile. So I'm going to draw a Cl minus. What's the first step in an SN1 reaction? Yep, the iodine is going to fall off. All right, so we've kicked off that iodine. That's the first step. It's rate limiting. And we're going to show a carbocation. And I'm actually going to show it in a particular way. And you'll see why in a minute. Oh my goodness. Let's see if I can do this. All right, so if we think about it, oh man. I'm trying to think of a good way of showing this. I think I was outsmarting myself here. I'm going to actually redraw the starting material. No, but I'm going to keep it the same. I'm just going to draw it in a different orientation, and you'll see why. If you want, you can just make a note right below. So this is still R, right? Do we agree? I just kind of flipped around the orientation of this. And in the first step, we're going to kick off this iodine. So this carbon is going to be positive. The iodine, when it popped off, it's going to pop off from that side, right? So it's going to be hanging out kind of underneath. And then we've got Cl minus over here. An important thing to remember about a carbocation is that it is a carbon that has an empty p orbital, right? So let's even draw in that p orbital. I'm going to erase this and show our p orbital using a p orbital lobe. Right, so you have a top face that's missing electron density and a bottom face that's missing electron density in that overall p orbital. All right, in the next step of this reaction, though, we've got some decisions to make. As a nucleophile, you have an option of attacking this top face of the p orbital lobe or the bottom face of that p orbital lobe. So let's draw both potential products. Right, so the chlorine could attack from the top, and our leaving group could be hanging out over here, or our chlorine could attack from the bottom, and our chlorine could be right there. What's the relationship between both of these? Are they enantiomers, stereomers, constitutional isomers? Are they identical? Let's go ahead and assign stereochemistry. For this top one, what would the stereochemistry be? For the top one, is it R or S? I would say it would be S, right? So we've got an S stereocenter up here. Let's take a look at this stereocenter down there. What would that one be? It would be R, right? The chlorines are coming off of the exact same carbon, but the stereocenters are opposite of one another. So what's the relationship? Enantiomers. So we would get a mix of enantiomers. All right. So let's think about this abstractly. Which enantiomer do you think will be favored, or do you think will both be favored? Meaning a 50-50 mixture. Is it going to be racemic, or is the S enantiomer going to be favored, or is the R enantiomer going to be favored? I'll give you a hint. Consider your leaving group. Where's your leaving group in that intermediate step? It fell off that bottom face, so it's still hanging out near that bottom face after it falls off, right? So do you think the chloride ion prefers to attack from the top face or the bottom face? The top face, a little bit, right? That iodide, when it falls off, is kind of wandering around. It's not doing a good job protecting that carbon anymore. So that chloride can attack the bottom face or the top face. However, it's a little bit easier to attack the top face. Yep.
Would it be able to attack the bottom just out of sheer electronegativity?
Yeah, I mean, carbocations are so amazingly unstable, that chloride wants to get in there bad. The problem is, if you attack from the bottom face, it may happen to run into that iodide because that iodide fell off there. Yeah, so let's make a note that SN1 reactions result in a mixture of stereoisomers in this example we saw it gave us enantiomers. In other examples it might give you diastereomers with a slight preference towards inversion of stereochemistry. And what I mean by that is you see how our final product, the chloride, was attached to the opposite face that the leaving group was on. We call that inversion, right? So it got installed on the opposite face. Retention would be where this iodine is replaced in the exact same orientation with our new nucleophile. In this case, we said that retention isn't as favored as inversion. So essentially it means the chloride wants to attack the opposite side of where that leaving group was originally on. Does that make sense? Yeah.
When you say slight preference, like is it like a quantifiable amount, or is it going to be like?
It really depends on the reaction system. So he was asking, is it a firm amount? Like, is it going to be 45-55, or is it going to be 60-40? It really depends on the reaction system, the solvent, the temperature. There's a lot of variables in there. All right, so that's where we're going to leave off today. Tomorrow when we come in, we'll look at the stereochemistry for SN2 reactions.